Okay, thanks so much. First off, I'd like to know what you guys want to learn. So is there anything in instrumentation, what is it that you really like to learn about? I've got a little thing here. What do you want to learn? Can you share with me what you're curious about?
Practical applications.
What's it, practical applications? Oh God, you came to the wrong place. Okay. Any other specific things? Anything else that just like, oh, I really want to know about this. I really want to know about that. You don't give a damn, you just have enough coffee in you to keep awake. That's it, okay. Well, anyway, blurt out if anything comes to mind. So let's just start big picture. If we're talking about instrumentation and we're saying we're doing an experiment, and the very first thing that often comes up is, my God, this thing, they're charging $5,000 for this thing I could make for $25. And that's your first hint that you're in the wrong direction. So that our goal when we're doing instrumentation, the instruments in the field, if they do what you want them to do, the chances of you being able to make them more economically in a reasonable time frame is very low. And I've seen over and over people think that they're going to be driven by economic opportunity, and they end up 2 years, 3 years down the pike with crappy data. So watch out. If that is your first and foremost thing, stop. Okay? Because that's just not a great motivation. So the second thing is that you should be looking out of the box at your data. What's wrong with these data? What's really limiting me in terms of what I'm doing? Is there some factor that is like really inhibiting me that everyone's experiencing? And this is what I kind of generally characterize as the adding zeros. So sometimes if you can add a few orders of magnitude of precision in a particular area, it will be transformative. It'll allow you to see new things. So that's really what you're looking for, is does the current instrumentation limit your ability to test your hypotheses? And if that's the case and everyone else is experiencing that and you have a way to get around it, then this is something quite interesting. So I would just first off get into the right frame of mind. We're going to talk about several things today. One of them is going to be kind of just thinking out of the box, so how new instrumentation concepts. Then we're going to take a little bit of a deeper dive into what if you had a technology that added a lot of zeros, so in other words adds resolution in space, resolution in time, and perhaps even resolution in quality of data. If you add zeros, what types of things happen? And what you'll see is that there's this kind of explosion of opportunity that occurs when there is a technology that adds a lot of zeros. And then finally, we'll just say a brief thing about this African work where we're doing sensing. So what we see in the marketplace is very sluggish development of new tools. And so this ISCO sampler is nearly identical to the ISCO samplers I encountered that were broken when I was in graduate school. That was in '87. They have not changed. These are open bottles, pouring water in open bottles and leaving them for a month. And it's like, what sort of quality data are you going to get out of that? And then they have these multi-sons, which sounds very fancy. It's the same old crap, just put more of them in the same package, and they basically drift and all sorts of other things. So there's really a sluggish development, and that's because we're a pretty small market. So there's not a huge amount of drive to fund research in this area. So it's also, keep in mind who's driving this. So why does ISCO make these? And it's not for us. This is for the wastewater industry, or the non-point source pollution industry. So there's these industrial clients that are actually quite important. So at that moment, the opportunities for advancement are crazy. And as we'll talk about, we really, there's all sorts of exciting new instrumentation out there, exciting new opportunities. But how does it really go? So how it really goes is oftentimes we have a student who needs to make some measurements, they make some measurements, they diddle around a bit, they come up with a new instrument that works for 100 measurements, and then they write it up and it's gone forever and no one can reproduce it. And so one of the things I'm thinking about a lot these days is how to make a community of development. Can we actually, using GitHub and whatnot, make a community of development where we don't lose all this stuff? How do we capture the developments that are actually going on? And so we do a lot of design by scientists. How do we engage engineering into this? So actually, scientists find it well, but these engineers have a lot of robustness. They look at reproducibility. They look at manufacturability, all sorts of other things. And so we want to be now collaborating with the instrument designers. So now you might kind of say, well, that's all fine and well. We all know there's all sorts of fun things out there. But I want to just give you one example which I think illustrates to some degree the magnitude of the opportunity involved. So in terms of a gravimeter, we could get groundwater presence and quantity by looking at gravity. And traditionally, we're looking at a couple $100,000 or so for a super cooled magnetic approach. But back in 2016, the guys up in Scotland came up with this very cool engineered microelectronic device that essentially had this very, very well calibrated spring, and they could get data which was very much consistent with the data that you'd get from a $200,000 device, but from something the size of a sugar cube. And now they're supposedly coming out with a product right now from it. You can look on the web. But if we were able to put groundwater monitoring stations that were $1,000 each, no well required, and you could actually monitor a few centimeters of change of stored groundwater, that would be transformative. And I think that in your lifetimes and in your careers, this is the type of stuff that's going to happen. We're going to have completely different strategies for looking at many of these variables. So the other thing, though, is this idea of collaboration. And so, as you all know, maybe you do, I don't know, I didn't, but when you do a 3D design of an object now, or a circuit design, you're basically creating just a simple script. It's a simple code that has all the parameters. And so anyone then can email that very easily or get it on GitHub, and you can make your modifications. And you can put a branch, and you can have multiple design developments going on in parallel. And you can share them very efficiently and have a community of development. I think that's just crazy cool. Now the thing is, it's actually a challenging thing though, is how do we actually make this happen? How do we actually engage people and make these developments occur? And oftentimes this, and what we're finding, is that this is much more of an issue than is the concept. So how does it actually make it happen? So I'll talk a little bit about that, and that's one of our steps forward there. Obviously, the sensor technology, as I just mentioned, are really a big deal. And then, of course, everyone knows about Arduinos, and the idea that you have these building blocks that allow you very high-level aggregation of sensors, data systems, telemetry, et cetera. And so that makes it accessible, whereas when I was your age, this was not really feasible in one graduate experience to be able to make something that actually would get the data out. So this telemetry is again, not to emphasize my age, but when we, my friend Jan Bull and I went to the field and we forgot our pencil and paper. We literally memorized 100 data points in the field. It was a nightmare. We're sitting there, like, okay, Jan, repeat after me. 3.256. We going through the numbers, and we bicycled back and we wrote them all down. There were dinosaurs wandering the earth as well. But anyway, in our case of African climatology, so we have 700 stations across 23 countries in Africa. How much, so we get hourly, we take 5-minute resolution data, we ship it up hourly to the web. Okay, how much do we spend per month, per station on telemetry? 25 cents, now we're at 25 cents. 25 cents a month. And I was sitting there memorizing numbers and running around on my bicycle. And this is like in Chad, and in DRC, in the Central African Republic, we have these stations going, and it's just incredible to me that for a quarter, I get an entire month of data just shipped right to me and right to everybody. So I think this telemetry is not to be underestimated. The power of it has yet to be fully exploited. This is really something which is going to change the way we look at the Earth. Can you expand on that, John, about the telemetry? Well, so yeah, So we're just using SIM cards. So we're just using in Africa, it turns out that the cell phone was hugely revolutionary, that they didn't have hardwired phones, and they kind of leapfrogged to cell phone technology, and then everyone got totally addicted to it, and all you see is these guys always walking around on their cell phones, and it's really a huge deal in Africa. And so they put in a density of cell phone towers that's well beyond what we have in the US, for example. And so in almost every little village, we can employ the local cell phone network. And so that's what we do telemetry. But as you, I'm sure, know, there are gazillions of Starlink satellites and other satellites floating around that are going direct to satellite. And so there's the LoRa to space, for example, which is a low bandwidth protocol. And so now every 3 hours you can send a LoRa to space for a few pennies. And so it's still not as cheap as the SIMs that we get. But it's the huge advantage is that it's everywhere on Earth. So for example, Somalia is a real problem for cell phones. And so Somalia will probably use direct to satellites. So there's several networks of satellites. Iridium was the kind of the first one that was put up in the 90s. And then Starlink went up, and then now there's all these LoRa to space that are going up. And they're successively lower cost. And you choose your satellite system based on the bandwidth you need, obviously, and the repeat frequency that you require. Is that what you wanted to hear about?
No.
Okay. Okay, so that's all fine and well. You know, all the ingredients are there, but what really can we do? I think it's a good question. So I want to just talk about a few things just to kind of get your head getting out of the normal box. So I was on a PhD exam. Well, first, this is Canada. And what's happening in Canada is there's a complete stand replacement. So the climate change, we have these pine beetles, they're killing all the pine trees. And any of you, so canopy interception. How many of you have heard of canopy interception? Not so many. Okay, well think about it. So you have these plants, and what happens, if it's raining, where do you go first? Under the tree. Right? Wow, you guys all understand canopy interception much better than you thought you did. So canopy interception is incredible. So what is a typical, who lives in some part of France here? What's a mean rainfall event in Rennes? What's a typical rainfall event size?
100 millimeters
per year. Okay, 700 millimeters per year. And we're going to divide that by 100 days. That'd be 7 millimeters per day if we just looked at the average. Guess what? A lot of trees can hold 7 millimeters. And so, standing on the tree is not such a bad proposition. If you have a stand replacement here, the thing is, for example, cedar trees have segmented leaves, and they can hold a lot more water than pine trees. So in Argentina, for example, I don't know, I'm going on a tangent here, but in Argentina, we found that you could explain the non-native pine trees were fixing way more carbon than the native cedars. And it turns out it was canopy interception. The cedars were fighting everybody else. They said, forget it, you're not getting any water. And so they were just taking all the water, holding it in their leaves, whereas the exotic pines just let all the water fall, so they would get it, and they would have higher carbon fixation, higher growth, which meant it seemed like higher water use efficiency, but it wasn't higher water use efficiency. It was the same water use efficiency, just less canopy interception. So in my area, there's the Columbia River, which is fed by this whole forest. And when that forest changes its canopy, it could change the groundwater recharge by a factor of 2, factor of 3, because groundwater recharge is a very small piece of the overall water budget in many cases. So I was on a PhD committee. They were doing it by these crazy means of hundreds of rain gauges under trees, and some of them get a lot of water, some get none. It was a pain. And then they cut down the trees and they'd hang them by a crane. They have a tree hanging by a crane with a load cell, and they sit there with a fire hose spraying it, and then they weigh the tree. It's like a poor frickin' tree. You can't really reproduce this experiment. It's like dead. Anyway, how can we do this with a non-destructive approach? And so I was sitting there in this PhD exam, diddling as usual, and I thought, why don't we use the stem of the tree as a load cell? Because it's a linear compressive material, so let's just put quartz rods around it, and we can use these little displacement sensors that are good to like a half a micron, and we should be able to put 3 of them around, and then take care of wind effects and blah, blah, blah. And so what you do is you hang bottles of water from the tree to calibrate it. So you see what's the displacement, how many microns per kilogram. And so this is our calibration, and you can see we change it gradually here, and this is like 20 kilograms, et cetera, at 40 kilograms, and then so we can see about 5 kilograms in this particular tree. And so we calibrate, And then we went to Africa, and here we're calibrating the tree. It's a pretty big tree. So we have heating blankets that hold our quartz rods exactly constant temperature, even though quartz is supposed to be not very expansive. But the tree trunk is. That's the problem. But anyway, so we ran, and then you could see actually a storm. And so this is the mass change interpreted, actually. So it goes down because of the compression. But basically, we captured 200 kilograms of water in this particular event, and it all evaporated off in about 4 hours. So it's really fun to be able to actually watch the canopy interception. Now, this was incredibly difficult because everything about it. How to mount everything up so it's perfectly centered, how to keep the temperature constant. It had to have really good data loggers to get the really good resolution. Everything was a total pain. And so we said, well, maybe, so it's actually doing some geophysics, and we were working with Fred DeLuis's colleague, John Lane, and we had these really cool little passive seismic things. And these are really amazing, so I was hoping that maybe some will talk about them, but you sit them down, and you sit there and just wander around, and the vibration, you report it, then you can deconvolve and get the stratigraphy just using native energy. You don't have to do any seismic. And so we had these amazing little things. They're made in Italy, I think. And so the question was, what can we do anything fun with them? So we're sitting under a tree in Chile. And I said, what if we nail it to a tree? What's it going to tell us? I was like, well, and we start talking. Well, it'll tell you the resonant frequency of the tree. But if you know the resonant frequency of the tree, that's a function of the mass and the spring constant. Oh, so now we can take measure the resonant frequency just being buffeted by the winds or whatever else in a passive way, and then do a Fourier analysis, and then see the offset in the spectrum as a function of mass. And so that we actually infer exactly the mass. And these little accelerometers now, you don't have to get the nice fancy Italian seismic thing. Actually, a 16-bit accelerometer is like $50. It has the little coin battery, it's got the SD card, you just nail it to the tree, and you've got a data set. It takes 100 hertz data, which is just plenty. So this is my backyard, and this is my 71 kilogram weight that I jack up into the tree and jack out of the tree and play with it to see if I could calibrate the tree. And indeed, we were able to, and the offset was pretty dramatic. It was about a 30% offset, or if more than 30, it was like a 50% offset. When we do the math with my calibration, a 240% change in mass of the tree from winter to spring when it was fully leafed out. So we can use it for phenology as well, but we can also get canopy interception. So this is now there's a company that makes these things. So if you want your own tree accelerometers, I can send you to Jim, who makes the tree accelerometers, and he's installed them in Brazil and in Europe and in the States, and it's kind of a thing. Okay, so what? Yeah.
When you were showing the strain with the loading before the accelerometer.
Yeah.
Go forward one more. No, sorry, backward too.
Well, am I going backwards? Is that forward or backwards?
Yeah, that's good. Keep going. One more.
Okay, that's actually forwards.
Sorry. The spike, the decrease in mass right before the storm event.
This business?
Yeah, what's that? Is that real or is that?
It was probably wind. A lot of storms are preceded by wind. And so then you get more noise in the system because we're basically, we take all the 3 quartz rods and we're saying this one got longer, this one got shorter, this one got longer, this one got shorter. And so what happens is we just have a big noise signal right prior to the rain. Yeah. Okay. So what I want you to do from that is say, look, you're faced with a problem, canopy interception, and can we do something different? And the answer is absolutely yes. And then also moving from what we've done already, now MIT, you've seen the guy who does a video interpretation of mechanical systems. And so basically you can take a videotape of a canopy and then actually infer the spring constants and everything for each tree. And you can actually do a whole ensemble of a forest and the canopy interception at the whole forest level, which is really, I think, where this should go. So anyway, I want you to think out of the box. I want you to, if you're faced with a tough problem and you find yourself putting hundreds of rain gauges out, think about it. It's like, well, maybe, is there a different way to do this? And just kind of stop, back up. And one of the engineering tricks we do is we say we will not get out of our chairs until we have 10 good ideas. or at least 10 ideas, maybe good ideas, and just keep on writing. Force yourself to just say, what else can we do? What else can we do? What else can we do? And that starts to open up the process of thinking about when you're faced with a problematic measurement. Okay, so I was supposed to, in Switzerland, understand the melting of snow. And I'm not going to talk anything about melting of snow, but they want me to measure the temperature of these glaciers very, very accurately and understand exactly the temperature dynamics of the glaciers. And I had seen that you could use fiber optics to measure temperature. And so I called up the guys in England. I said, hey, can you bring your instruments over? I want to see what this does. And they did. And so they brought this instrument. We played with it. It's like, this is really freaking cool. And so what it is that you shine a laser down a fiber optic and you get this scattering. And a couple things happen. You get some really close bands that move in frequency. Those are the Brion bands. And then you get other bands that change in height when the temperature changes. So basically when you blue shift, that means you're getting photons which are more energetic than the ones you put in. And that indicates that the glass is at an excited state. And so the warmer it is, the more the glass is at an excited state. So this peak, it turns out, is very sensitive to temperature. And so if we take the ratio of this peak to this peak, which is not temperature sensitive, then we can normalize out the attenuation of light that happens down the fiber. So we send a pulse of light down the fiber, we look at the resulting backscatter, we look at it in two different frequencies, calculate the ratio, we've got a temperature, and using time as a substitute for space, we can then assign, based on when it arrived, where it was down the fiber. Okay? So it's a very cool little technique. This is my daughter, who's now just testified at the White House the other day. So this is a little while ago, we can just say. But anyway, we went to the powerful Maesbeek River in Luxembourg, which you can jump across in one leap. And we took a bunch of data. We just laid the cable in the river and started from the headwaters and went down and laid the thing in and honestly didn't know what we were going to see. And what we saw was there were these breaks in temperature where it would get a day, it would be night, day, night, day, night, day. These are days here, and it gets warm in the day. And then at this point, that stops. Well, basically, this is a groundwater emergence. Okay, and we can calculate, based on this change in the diurnal fluctuations, you can calculate how much constant temperature water went in compared to the fluctuating temperature water. So we can actually do stream gauging right down the river and get the exact contribution of each of these inlets. And we can get the exact temperature of those inlets. And so we can start to see the spatial distribution of how a stream comes to be. And so one of the things that we often forget is that streams are really, in the summer like this, they are 100% groundwater. And a lot of people don't appreciate how this thing is just emerging from the landscape. So for me, that was really like a mind blower. And then we were called into the Walla Walla watershed. This is where our endangered salmon are. And so these farmers have been shutting off this river 100% for 99 years, and then someone said, that's not okay. These are endangered fish. And so we wanted to know where the fish hung out. Where do the fish reside? Do they reside where there's a lot of hyporheic exchange, which moderates the temperature fluctuations, or do they reside where there's a lot of groundwater emergence, which changes the mean temperature? So what are they looking for? Less fluctuation or change in mean? So here, basically, we took all these data and we quantified which were hyporheic, which just basically compressed the variation, versus which were groundwater, which did a displacement of, and then we were able to attribute exactly where the salmon lived. And the salmon actually liked both. But what they didn't like were reaches where there was no hyporheic nor groundwater, because then it would get too hot for them. So they just basically liked lower variance and colder. So we were able to basically swam the river, found all the fish, and we were able to see that yes, indeed, they want really heavy hyporheic or groundwater emergence. Those are their favorite things. Okay, so we can see that. So now we're looking at this technology, and I can take the temperature every basically 25 centimeters, and I can measure it to about 1/100 of a degree. And I can do that I can make a measurement every second. Then to get the 1/100 of a degree, it'll be maybe 10 minutes to get a good measurement. But every second, I can get 0.3 degrees C. So it's like, well, what else? So now we're faced with this really cool technology that was good in my little but I'm a Vado zone guy, and I was like, well, what can I do in the Vado zone with this? This is, I'm done with the snow stuff, sabbatical's over. So we said, what if we heated this cable? Wouldn't we know the thermal conductivity and the heat capacity of soil is strongly dependent on moisture content. So would we not be able to see distributed moisture content in the field? And so we put in TDR probes and we put in a boundary condition at the bottom. We made a little column here. And basically this is of course what we saw was that in very dry conditions, if you put in a heat pulse, we're putting in 10 watts per meter for 4 minutes, you get a much bigger deviation in temperature than when it's very wet. Not a surprise, right? The interesting thing is, this is where your mental model often can be a disaster. So this was done before we did this some time ago, but the guy who did it said, well, I can project back to here and use the intercept, because there's some differential equation and the intercept would give a certain ratio of parameters. So he said, I can get the intercept, but there's so much noise in the data that you can't distinguish these two curves. And it's like, we just looked at it, it's like, I can distinguish those two curves. and so don't let your model fool you into thinking you can't do something that really you can do. And this is not uncommon. And so all we did is just integrate under the curve. What the heck? It looks like the obvious thing to do. It gives you all the noise reduction of averaging. And so here is the area under the curve versus moisture content. And it's like splendid. That's all you need. And you can derive it if you want. It's not hard to derive what you should expect. But don't go to there's all these standard analytical methods that people use to interpret these things. And oftentimes they'll lead you exactly into a hole. Okay, so then we can go out to a cornfield. And this cornfield had the irrigation system going right into the corn stalks. And so it had these really pronounced areas of infiltration. And so here we can do a time series looking along that distance. So we're looking at 240 meters, and we can see these very distinct places where the moisture content increased dramatically in time. So these are different times, and this is at the 60 centimeter depth, and this is, I think, no, it's a 30, and this is 60 centimeters depth. And so you can see that this is problematic, that they're getting deep percolation under this irrigation system. So anyway, wow. I mean, to some degree, if you're a Vado zone guy, this is kind of my definition of the Holy Grail. I can now see the moisture content distributed in space, in time, and I can associate it with processes. Super cool. Then the atmospheric scientists get a hold of you. They say, well, John, you did this thing with this moisture content. Well, couldn't we do a hot wire anemometer? So a hot wire anemometer is where you just heat a little piece of metal, and if you blow on it, it gets cooler, surprisingly. And so why don't we do that with fiber optics? We're going to take these little fiber optics that are in a 0.8 millimeter stainless steel tube. It's the same technology as injections. So we've all been through COVID. So those little needles you made were made from wrapping a piece of stainless steel in a circle and then laser fusing it. And so we do that with a fiber optic in the middle. Now we have this little tiny stainless steel pipe, and we're going to put some high voltage across it, and then hopefully, well, you put little flaggings, do not touch. So we're often working at high voltages, and so this is kind of one of those things that you care in the field. You have to have everyone. You really have to watch this. Don't let it run without anyone there. So anyway, we put them at 3 elevations, and then we put a heated fiber and then non-heated fibers. We have to take care of the fact that the sun shines on it and things like that. But this is what we see. So this little valley in Colorado. So the north side versus the center versus the south side, I mean, look at the temperature contrast we had here from 0 degrees to 10 degrees. I mean, look at that contrast. So what was happening is that there was a clear night, and this air was sloshing back and forth in this little valley with these, you feel it just like hit you like it's cold wave and warm wave. But to be able to actually see that in space and time is just really, really exciting. And so then we said, well, how would we know the velocity? Well, we're going to heat up our cable so we get a delta T, and then we solve all the equations, and you can basically get the standard hot wire anemometer equation. And so when you have low delta T, that means you have high velocity. When you have high delta T, that means you have low velocity. So no, this is high delta. Yeah, high delta T, low velocity. So you can actually see the different regimes of airflow in time and space. So you might want to compare that with a sonic anemometer. So we put sonic anemometers distributed through the system, and we got correlations of like 0.9 something or other. It was ridiculous. So we can this is the sonic laid on top of our data, just taking one little point of our fiber optic out of thousands of measurements, and actually we can reproduce the sonic anemometers pretty well.
John, what is a sonic anemometer?
A sonic anemometer. That's a very good question, Danny. It's a thingy. So does that help? No, a sonic anemometer, it basically is a device that sends a pulse of sound, and it receives the sound, and then based on the time of flight, it tells you the velocity. So you can put a three-dimensional sonic anemometer, it can tell you the velocity in all three directions using the speed of sound. Yeah?
I'm sorry if I missed this. Is the fiber optic cable in the air? Like what height?
Yeah, so we're at I think it's like at 51 and 2 meters, is it? Yeah, so we're just showing the 50 centimeter and the 2 meter elevation. Yeah. So now, and the other thing we've done recently is we can put little cones on them. And so we put little injection molded cones on our fiber, and we can actually have them be asymmetrical, and we can actually see the direction of the wind because they leave a kind of a trail of influence as you try to heat the fiber. So this is ongoing work. Here is, you're looking at, and this is again, remember the sloshing? So there's this really interesting, these buoyancy oscillations that happen with air. And so this is, looking at the wind speed as, over a 200 meter section at all points at two different elevations. Isn't that fun? So it's, and I think kind of a game changer in terms of understanding turbulence. So, okay, we've done it in soil, we've done it in air, we've done it in glaciers. So what about water? So let's go to the Dead Sea. Now, the Dead Sea has changed a lot. It's evaporating. The stratigraphy of the Dead Sea, it didn't used to turn over. Now it does turn over annually. There's just things changing out there, and really we want to understand what's going on. And so what we need here is a really high resolution vertically. Now our fiber optics are only good for 25 centimeters mostly. So what we do is we wrap the fiber around a core, and we can put like a 10-to-1 compression. So we can now go to 2 centimeter resolution. So we take this is our little thingy, our buoy, and we vertically have a 50 meter long high resolution probe. And now we're looking at the structure of the stratigraphy in time. Early in the season, it has this very kind of slowly changing, fuzzy interface. But as the season goes on, that interface goes down to 2 centimeters. The cold, whoa, what's going on here? So what's really cool, and here, see those, this is, now we want to understand, so we put a camera down to actually watch at that interface. And you know what happens is it's a double diffuse problem where the diffusion of heat is relatively fast compared to the diffusion of salts. So at the interface, the upper water is super saturated with salt because it's been evaporating and it's really warm. And the lower stuff is just saturated with salts and it's cooler. And so the thermal energy goes up, cools off that really hypersaline stuff, it becomes denser and it plunges in fingers, okay, which is all fine and well. But the really cool thing is, to me, is that then the salts precipitate because they're so super saturated that they actually snow. And so inside of all those fingers, it's actually snowing, which actually amplifies the density fact because you go to a solid in solution. And so it's kind of hyper unstable, if you will. So anyway, that has been fun. And so we wrote a couple papers. This whole, our little buoy, well, first off, haven't any of you been to the Dead Sea? Okay, so the Dead Sea, I hadn't either. And I'm out there, and that's all fine and well. And, but it's slippery. So you remember it's slippery as the dickens, we can say, to be in a polite conversation. But so it's very slippery, and so but you don't need life preservers because you float, right? And so, but then a helicopter comes in and takes a body away. And like there's these tourists on the beach, and one of them just dies. And I asked them, that's just not like you really want to have happen. And so I asked my guy, I'm out there, in the middle of the Dead Sea, dinking around stuff. I said, what's the deal here? What happened? Why the helicopter? He said, oh, the guy died. It's like, well, okay, why? Well, John, if you let this in your mouth, this water in your mouth, your esophagus immediately collapses and you can't breathe. So it's game over. Okay, now you tell me. And by the way, he said, if it gets in your eyes, it burns like acid. And so, if you fall in, focus on two things. Close your eyes and don't let your mouth open. Okay, so, but it's just totally slippery. We had these little pieces of wood we're walking on. It was like, whoa. So it's kind of, but that, and the whole thing sunk. Everything in the Dead Sea sinks because everything precipitates salt and it pulls everything to the bottom. That's why there are no boats on the Dead Sea. Anyway, okay. Now, another basic question in hydrology is this relationship: where does this groundwater emerge into the surface water? It's a really important question. And when you're in the surface water, it's really hard to say. And so what if you took a whole bunch of fiber optics and laid them in a pattern in a couple of different bays here and see, do we see anything in terms of where we would see emergences? And so, we'll do a couple weeks of measurement. We use side-scan sonar and stuff like that to help us. But one of the cool things that we can do is if you have an emergence, it actually suppresses variation and it gives a local depression in the temperature typically. And so the cool thing is you have so many measurements, because we can take the data every few seconds, we can do tremendously powerful statistics. So we can actually do the statistics on every point along this fiber and see where it doesn't, where it pulls out seepage. And here we have the seeps identified. And then you can go back and verify them, which they work out well. The other cool thing is that when the tide goes up, the seepage is down. And when the tide goes down, the seepage is up. And so you'll see that the temperature variability in the low tide and the high tide is totally different. So it's really fun, and that also helps you identify where the seeps are really occurring. So now we can map, large scale, the seepage. We also might want to know not the seepage up, but the seepage down. That's harder because we don't, for a variety of reasons, your temperature variations are not as persistent and more complicated. But if you go ahead and bury a bunch of fibers, and we're going to heat this one, and then we'll see the advection of its heat away from it. So we go into a wetland, and we're going to look at the loss of water. And again, what you're here doing is you're looking at a thermal model for a heat pulse. And so you look at the thermal model, look at the delta T, and that should give you eventually the velocity of the water. Okay, so the interesting thing was, so how many of you have been told that hydraulic conductivity is logarithmically or log normally distributed? Okay, hydraulic conductivity is logarithmically distributed. Okay, that's solved. But the thing is that that's what everyone told me. And so I thought that we went to this wetland, we're going to have these big places which have high fluxes. But the curious thing was, there was one that had approximately 2 times, this is 30, that's 50, had just almost twice the flux, but that was the limit? Well, the cool thing is these wetlands self-heal. So if you have high infiltration, then it brings a lot of biological material and it basically clogs it up. And so the wetlands appear, in my book, to not follow the patterns of hydraulic conductivity you'd see in dryland soils, but in fact are healing themselves and creating a more uniform hydraulic conductivity, which is really great news in terms of water treatment. So this is a water treatment site, and we were really worried about preferential flow, but it turns out, it seems here, preferential flow took care of itself. We can also, those of you looking at boreholes, this is work done with Rennes and Olivier Bourg and Tanguy. And so we made these long cables that had a heating, so you have one big power cable so we can deliver energy, and we heat these cables, and we have reference cables, and we can then look at the delta T and get the velocity of water locally. So here's our delta T versus velocity, so we can actually get the borehole velocity of the water. We can also, and again, I give you warning that if you play with John Selker, you may get electrocuted. So they had a teapot. And I said, how about if I break that teapot? And so I took the teapot and zip tied it, the heater, to our cable and put it down the well. And then you'd plug in the teapot and create a heat pulse. And then you could then turn on the pumps and you could start to see the actual advection velocity within the well from a point source, which was kind of fun as well. And then that teapot method we said, well, what if we did that in kind of like at a larger scale? So we actually took fiber optic cable and wrapped heating around it in little pulses. So we made a 600 meter long cable. Every 2 meters it had a intensely warmed area. We call it the dotted line approach. So we have here on the order of 200 to 300 little heating spots. And each one has its own character. And so we can get the local heating, but also so we can see, we can learn a lot about the local velocities. And the cool thing about this is that you also see asymmetries in the heating. So you have this heating spot, and is the heat advecting upward or heat advecting downward? So you can actually get local velocities. So we patented this actually, and so it's not widely used yet. But another question you might ask is geomorphological. So one of the really interesting questions in sediments, and this is very important to you guys. So how many of you have gone to the beach? Okay. Go to the beach, forget the lectures. So anyway, but it was some years ago that there was way more sand at the beach. And then the sand went away. This is important to us. So this is a locally important problem that the sand keeps on coming and going. How would we ever be able to see sand movement or geomorphic movements in rivers? And so what happens is, what if you had a driving temperature of your surface water that was perhaps chaotic? Don't ever tell me that surface water temperatures are sinusoidal. Particularly if I'm your reviewer, X. So they're not. They have some sinusoidal-like things, but is that sinusoidal? No. So then what you'll do is just run a thermal model for that boundary condition, run a thermal model, so then you run it at all different depths. And I just use that boundary condition at all different depths, and I have these different data. And then all I have to do is match up which of these lines matches best to the local observed temperature, and then I can say, well, it must have been that deep. And saturated material has fairly tightly bounded thermal properties, so you can actually be pretty good at that. And this is Cargès. These are data from our beach. That is Olivier, I think, or is that me? Anyway, I mean, it is me. Anyway, so we're out here. That's Olivier. He's in the kayak, and so we're out there burying wire, burying cable, and then here's our boundary conditions. And so we simulate it. And so this is the surface from zero depth burial all the way to great depth and how it smooths out. And then basically we fit each one, and we went out there with a ruler. So with masks and a ruler, we actually measured the depths of the cable. And so those are the blue line, and these are data which you shouldn't, like we were doing the best we could, but we were literally paddling around trying to do the ruler. And there had been a big storm, and so it had moved a lot of sand. And so you can see that our inferred depths versus the observed depths, not that bad actually. So you can now watch geomorphology of rivers in real time. So, okay. So, how am I doing on time? Am I like totally out of it? How much more time? I have another half hour? With questions. Right. Yeah.
You have still a bit of time.
Yeah.
Can you clarify that just for a second? So you're, if you think about doing this in the river,
yeah.
Your temperature boundary condition is you're assuming the water is uniform temperature up to the bed?
So we measure the temperature in the river itself. Okay. We either use data loggers or a fiber that's returning that's not buried. Okay. So we get the upper boundary condition one way or another. Yeah. And then and by the way, that's fairly homogenized in rivers because there's a lot of turbulence and stuff. Yeah. But anyway, so you can measure it, you don't have to have every 25 centimeters. Yeah. But yes, and then we bury the fiber oftentimes at an initially known depth. But then as the sediments move, they change their depth, and then you can watch the dynamics of the sediment depth.
Okay.
Yeah. Okay. Is there another question? Ah, yeah.
So for the fiber optic application to borehole for fractured aquifer, can you use that for getting lateral flow information?
Yeah. That's the Wren group. That's their main concern in life.
Using fiber optics?
Well, no, getting fracture fluxes.
My question was using fiber optics, like can you heat up locally and then see the dissipation and get the lateral flow, for example?
Get the lateral flow?
Yeah, lateral flow, not the vertical
Yes. Yeah. If you, it depends on if you packer it. So if you can either use one of those flute packers where you actually put a packer down and then inflate it and then do a heat pulse. You can grout it in and do that. And then, yeah. In an open borehole, it's a bit trickier. Then you can put in, little micro packers. But the real answer to that, which is really cool, and I wish someone would do more on, is you can use polyacrylamide gel. So Maria and Clement and I,
I still have micropackers in my office.
What's that?
I still have the micropackers in my
Okay,
office.
so the cool thing is there's this polyacrylamide gel. So what you do is you pour this polyacrylamide in the well, it puffs up, and in beads, and it completely gets rid of turbulence, first off, so you don't get any instabilities if you have local hotspots. And then it actually, if you use the angular PAM and you put a little compression on it, the conductivity goes down to less than that of a silt, like between a clay and a silt. So you can actually make it, you can temporarily packer it. But so you can then put the fiber in and then do a temporary packer, let the pressure off, and then do sampling. So you can actually go down and take your polyacrylamide and do analyses of it because it's equilibrated with the local environment. I just think it's a very exciting opportunity. Yeah. The equilibration for temperature, we take care of the fiber optics, but for chemistry, if you want to know the geochemistry of your site, you can actually go down and grab these things that have sat there for days, and you can actually get localized chemistry with no mixing. I think it sounds, to me it seems interesting, but yeah.
For your sedimentary accumulation on top of the fiber, it could also be vertical flow.
No, that's very different. Our model, vertical flow is our main bread and butter.
Yeah.
And so we can get vertical flow independently. So you won't be fooled. No, the signal from vertical flow is completely different than the signal from burial. The vertical flow has a mean offset, it has no temperature, has no temporal patterns typically. It's groundwater, so it's very constant temperature. Those are easy to distinguish.
So you could invert for both?
Yes, we do. Yes. Okay. So now, I'm going to go really fast. I'm really sorry. A question.
Well, I have the question getting X as view from the reviewer about the sinusoidal temperature.
Have you experienced that on my part? I'm sorry. Okay.
Yes, the scale of the plot was very, I think, in months, right?
No, that was in days, I think. Was it months? Let's see. I forget. This is daily. So this is 29th, 30th, 28th. Is that sinusoidal?
Yeah, I mean.
No. I mean, come on. There's all sorts of. Look at this. There's drift. There's peakiness. No, that's not. It's asymmetrical. Okay, if it's good enough for it depends. It depends on what you're doing. For some things that's sinusoidal. For other things, it's not. We actually really like the texture of it. So and why the heck not? We'll just go ahead and simulate the whole thing. So no, there are times when sinusoidal is just fine, but it's one man's sinusoidal is another man's triangle wave. Is that a triangle wave? I don't know. Okay, so really quickly, what people do you think should be employed to develop new sensors? I claim that graduate students are not the best. Graduate students are easily distracted, they want to solve the world's problems, and they're in a big fat hurry. What we need are people who are very focused, who are ultimately patient, and who will just do as directed. So I don't think I'm breaking any mysterious bounds here, right? You know this. So anyway, so what I decided is that I should work with undergraduate engineering students to make new sensors. These kids, they give them a problem, they're like a dog with a bone. They just go, So anyway, this explains that whole dog with a bone thing. Okay, we have a philosophy, it's all open source, so that's all great. But we use a CERN S copyright, which allows us, we have 3 companies now licensing our work. So the CERN S is a really cool copyright. If you want to know more about it, we can talk about it. Here's a typical section of our students. They're 95% undergrads. We have 40 students working in the lab right now. This is their...
Explain about the lab. We don't know what you're talking about.
Okay, fine. Okay, see all these people? They go to a room. It's a lab. And what we do is we have clients, actually, who often are asking us for a solution. And so I take their money, and I hire some students, and I say, make this thingy. And then we work on it, and we work with our clients, and they make things. So we have about 20 different teams working on specific environmental measurement tasks. This has been going for 6 years. And everything gets we'll talk about more about it. The lab will emerge a little bit.
Yeah, and there are students with no name. Why is that?
Privacy concerns. Okay, so you can go to GitHub and see our different projects. This is a list of the projects and all sorts of resources. So you can actually get video training on all sorts of things. But each project has all of the designs, all of the code. Everything is published up. We have all these weird projects. We have a cosmic ray method for soil moisture measurement. We'll talk about the dendrometer, the eDNA. We have an e-greenhouse solution where we look at greenhouses. We have a hyperrail for moving around remote sensing. The evaporometer we'll talk about. We have calibration devices for rain gauges. We have RFID, soil moisture, et cetera, et cetera. Oh, and this one's really cool. The Pied Piper. We actually listen for leafhoppers. We do fast Fourier transform in the field. Listen for leafhoppers. With 99% probability we can find the leafhopper. We send out its mating signal and we draw it to us and take a picture of it. And anyway, okay, so measuring stress in water and plants is a really big deal. If you try to understand the water dynamics of an environment and you sit there measuring soil moisture, where do you measure it? Do you measure it high? Do you measure it low? Do you measure it close? Do you measure it far? But you have this very convenient thing, a plant, which is actually integrating a large volume. So why not just measure the stress in the plant itself? There's a couple ways to do that. You can stick something in the plant. They don't like that. They put sap into it. They will just defeat you each time. Well, if you just sit there and be very nice and measure their outside diameter, then they're actually reasonably acceptable. So what we're going to do is measure the outside diameter of stems and look at the dynamics of them. Now, if you look at the traditional technologies, and if you've used dendrometers, they're made out of aluminum and steel and things like that. What do we know about aluminum and steel and stuff like that? When the sun shines on it, it expands. And so we're looking for a diurnal signal that's in the micron level, and we're using materials that expand and contract. Problem. Secondly, these are all using mechanical plungers, and they have friction. And so there's hysteresis. So when it's going from expansion to contraction, which is exactly what we're looking for, it delays. No, I'm not going to tell you anything. I'm changing direction. So we want something with zero hysteresis, mechanical hysteresis, and zero thermal expansion, and it goes on easily. So we actually just got issued our design patent and the utility patent issues on August 9th. So what we said is let's use carbon fiber. Carbon fiber, as it turns out, has zero thermal coefficient of expansion. It's crazy. It's really cool. And then instead of using a mechanical plunger, what we did, we wanted zero friction. So we use a spring and we pull this side against that side of the tree, and we this side against this side of the tree, and these things are just floating above each other. And this is a Hall effect device which measures to 0.5 micron. And so we have zero mechanical friction, and we get 0.5 micron resolution, and it's great. Works like a charm. This is one of those places where this was all done with COVID. So I was advising a student over Zoom, and it's like, get me 10 ideas. And we'd sit there and talk through all 10 ideas, and then we'd go to the field and test them and refine. So we have 100 devices in the field now. They're working. They just got put into the Biosphere 2. So we're measuring plants in the biosphere and other places. It's really fun. The idea that we're using a license agreement that allows us to both publish it, patent it, and license it is fundamental. So we're looking to, there's a company that's going to license this, and that's going to have a big impact on the lab. Tracking ecosystems. If you think about water, there's DNA in the water. It turns out you can identify some, they say 5,000 organisms at a time. So you filter the water, you can look at the whole DNA signature. This is how it's done currently, where people sit with a backpack and a pump and they sit there for like an hour and a half filtering water. And this is very expensive. And so we were asked to make an automated sampler. And so this is a robotic eDNA sampler where it does a whole set of purges, and then finally it filters, it measures exactly how much water was filtered, and then it preserves it on ethanol, and the whole thing is over-the-air programmable with your iPhone. So this is a classic little undergraduate engineering project. It's taken us like 5 years, and then we made a COVID version of it and stuff like that. Anyway, transformative in the sense that we can take 24 programmed samples at remote locations, and they don't have to, the human just drops it off, puts it in the water, goes. And they just got deployed in Alaska like 2 months ago, and we got a month of data from there. Yeah?
Really quick question, what's the volume of these samples?
They're filtered, and so we have a flow meter right here. This is a rather expensive flow meter because it turns out it's really hard. So we are typically going between 500 mils and 2 liters. The filter, anyway, that's a huge problem. The filters, what size filter to use? The industry standard is 0.5 micron. They plug up really quickly. So then we went to like 4 micron filters. Then we can get 2 liters through them. And it turns out the literature is supporting the fact that you still get plenty of DNA. Okay. Rain gauges, how many of you use rain data? It's terrible. So rain gauges plug up. They have wind effects. In intense rainstorm, they get the wrong number. Other than that, they're great. And so why can't we do something more interesting for rain? I was in Cameroon, and in Cameroon, they get 10 meters of rain a year. And so I needed a rain gauge that took no maintenance, could do extremely high levels of rainfall, and didn't have some of these other problems about changing water levels and stuff. So what I did, I took a bucket with a siphon in it, and I pack it full of fiberglass. It presents a constant geometry device, no changes there, flat topped, and what happens is it fills up with water, and then it drains, fills up and drains. We put it on a load cell. You can then see the filling and draining, and you can get the amount of mass change. But the really fun piece is that after it's done and it gets sunny, you still have 7 centimeters of water here. So we can actually watch evaporation for about 10 days. And you can see at 5-minute resolution. This is a 24-bit system. So we can see, milligrams very easily. So we can see at 5-minute resolution when clouds go over, et cetera. So it's we call the evaporometer. And this is now, there's 2 companies that are going to license this. We think that we're in negotiations. I think this is going to be a game changer in terms of rainfall measurement. It's a complete disaster right now in so many ways. And so this is one way to do it. I'm sure there's going to be some other good ideas as well. Here is that you really want to push the envelope on some of these technologies. Isotopic measurements, if you're looking at isotopic signatures in groundwater or surface waters and you say that, hey, it's changing isotopic signature in time, you want to use these isotopic collectors. So you look at this is the standard. Has this long tube, has a plastic bottle. It's like a 4-liter bottle. So you take a little bit of rainfall, put it in the bottom of a bottle, and hope that there's not going to be isotopic enrichment. I mean, there's all this headspace. It's ridiculous. And it's in a plastic bottle. Plastic bottles are, how many of you left a water bottle accidentally for a year, you come back to it, it's all shriveled up? You tell me that these things don't have diffusion? So this is a terrible design, as far as I'm concerned. I don't know how the world came up with this. And they're very expensive. And so what I said was, why don't we use this, the military ready-to-eat meals, how do they keep them good for 10 years? They use aluminum, because aluminum has a very low diffusion coefficient. So you get these bags that have a thick layer of aluminum, they have almost no diffusion coefficient, and we just grab it in a funnel that has a little float in it, and so only when it rains it floats up and then it drops back down and seals. Okay, so this is our isotopic. Here's the data. So here is Mr. Tube. This is the loss of mass over time, over a month. And here is our little guy. So $25, $500. Anyway, so in a fairly simple strategy, using 3D printing, you can actually really solve some of these problems. The other really nice thing about it is that we can hold 50 centimeters of rain. So in terms of a check on precipitation, we're not losing mass. We can actually gather all the precipitation, because so many times your rainfall rates, as I say, when it's really heavily raining, you want a check on the total accumulated mass. Was there a question? You looked uncomfortable.
What's wrong with the oil method?
Oh, it's just a mess. Yeah, you can put an oil in, then the rainfall goes through the oil. And the oil method, yeah, so the oil method is down here. It's pretty good. It's just a frickin' mess. So, yeah, other than that, it's okay. The oil methods, yeah. Okay. So can we use undergraduates to develop technology? Yeah. Is their work transformative? I think so. I mean, at least I'm excited about it. Is open design sufficient? And this is the real bugaboo. No one will make our stuff. Everyone comes to us and says, John, will you please make me 100 of those? It's very disappointing. I was hoping that the community would say, oh, I just grab the design, we'll make it. There's like about 3 people who've done that in 6 years. So that's very disappointing. But I am a firm believer that ignoring reality is not a great strategy. So that's why we're basically going now to the commercialization, where we actually are going to license these things to people. No, not taking away anyone else's right to use those designs. That's all there. But we need to work with the commercial sector to actually get them in people's hands.
So why is that? Why is the 3.3 there? Why do you think
People don't make them? Actually, because they're smarter than I am. That's because they realize that if you make something like this, the chances of it working the first time out of the gates is pretty low. You have to know how to solder, you have to have a 3D printer, you have a defect in your printer, something da-da-da-da-da-da. Actually, it's smart to have people who know how to make stuff. And so it was a bit of I think, a dreamy-eyed interpretation of the world for me. Some of these things are, like the isotopic sampler is pretty easy to make. It's just a 3D print. But some of the, like the eDNA, forget it. Don't even start. I mean, that's a really complicated project. So it's actually, they actually are not dummies. This is reality. So it's not, so believe, that's one thing is when reality hits you in the face, learn. Okay. Yeah.
How do you commercialize something and keep it open at the same time? Is it easy to convince people to work with you to do that?
Yeah. The deal is that CERN, so the question is, how do you commercialize and keep it open? The CERN-S copyright says that if you use that design and you sell it, you shall publish each and every modification forever. Yeah. So companies don't like to do that. Yeah, they want to take it, modify it, make it, and say, no one else can make this because we made it so well. So the last thing they want to do is to have it published. So what we do is we say, fine. You want a license? You can license it to us. We're the idea creators. We're not constrained by CERN-S because we came up with the ideas. We can then sell the ideas to the company. They can independently continue development while still everything else stays online. Okay, and I'm sorry, we'll just go quickly. The Great Rift Valley, this is where we use, we go the capitalism course. So, capitalism, good news, bad news. So, you have to work with them with your eyes wide open. So this whole destroying the known world is really a problem. Okay, so you can join our ecosystem. I want to talk a little very briefly about our African work. So we have 700 stations in 23 countries with 10 years of data. And basically our idea here is that the density of observations in Africa went to 0 essentially. This is 0 stations per million square kilometers, okay? So that's 0, that's like 1, that's 2 per million square kilometers. The 1955 versus now-ish. It's worse actually. And then you say, well, let's just use satellites. Oh, great. So we took the satellites and looked over our rain gauges, and the correlation coefficient is 0.03, or you can say 0.04. So we can explain 4% of the variability, yes. And the slope is only off by a factor of 5. So as long as that's working for you, so the point is that all good satellite data are ground truth. So they pin them to an observation on the ground. In Africa, there's no ground truth, and the satellite data is completely useless, essentially. And what they did is they based insurance products on those satellite data because they had no ground truth. And guess what? The farmers were getting paid when they didn't lose anything. The people who lost stuff didn't get paid. So it collapsed. And so we really think we need to have on-the-ground measurements. And I guess the idea with the African work was to demonstrate a fully African implementation that was non-governmental. And so we made MOUs with all the governments. We said, will you allow us to take data? Senegal still has not said yes. Many governments did. And they have the big red button. They can turn our system off any day they want. So we give them autonomy, we give them control. But we're going to take, and we give them the data free of charge. And we give any researcher data free of charge. By the way, we have 200 teams using our data, so you can get it too. If you're going to publish. If you're making a product to sell or a product to distribute that's a product, no, then you pay for it. but the point is, we are taking data at approximately 2% of the cost of the World Meteorological Organization. And so we are trying to show that there is a way around our data dearth, and that we really think that we're trying to open the eyes. And now, after 10 years, we just had a really cool meeting in Nairobi. I just came back from that. And the world is changing. I think we're going to see a massive change in the way we collect this climate data. It's one of those things that they literally are spending hundreds of millions of dollars and getting nothing. And we're spending $300,000 a year and getting something. So, okay. So takeaways. The private-public partnership is really important. Work with the right talent. Have the right people do the right things. It's not obvious. We all think graduate students, but actually sometimes undergraduates are far superior. Hate to tell you. It is a broken marketplace for global monitoring of climate. There's $300 billion a year lost essentially due to lack of observations. And so I think that we have to see these things and react to them. We are the environmental people. We are the people who do measurement. And if we are not going to forge new methods, then who will? And then finally, dream and, so think up new cool ideas, but think of them in the social context, because the social context really is what's going to control your long-term success. Anyway, what I'm trying to do is just get you thinking about measurement, and I'm happy now to answer any other questions. And we have some minutes. No, we were a student actually. Yeah.
Quick question, what happened between 1955 and now that African data just disappeared?
There's this whole independence movement in Africa. So we had colonial control, and the Brits, one thing they really believed in was pencils, papers, and measurements. And so they literally from the 1880s, they were taking weather data in Africa. This is a very British and colonial thing that they've set up these stations. They were looking at the long term. They were looking at extraction, and so they needed to know the climate to do the best extraction. So then when the social structures changed, there was no longer a unified governance. It was a much more of a democratic governance. The first priority in the minds of the new governance was not let's monitor weather data. It's like let's stay in power, unfortunately. And so that's all that. Then you can see the results. Yeah.
So I'm curious about this fiberglass filled
bucket.
rain gauge.
Yeah.
So that's like basically putting a little lysimeter out there.
Yeah.
So how does the ET look?
We don't know. We have data for now a year next to a pan evaporation, and they seem to correspond quite well, but I haven't done the full analysis yet. One of the problems of working with undergraduates in this capacity is that they could really give a crap. In terms of the measurements, they're all about the tool, and so now I really do need a master's or graduate student to like dig into the data, because we know it's not like ETO, we know it's not ETR, we know it's not ET alfalfa. What is it? And so we do wonder, but we look at the correlation of the pan evaporation for those 10 days. It's quite close.
And I guess that was another kind of question / comment on this. I'm thinking about how, in hydrology, it's great to have all sorts of new kinds of measurements, but often what we need is long records and people using the same methods so that we can compare across space.
Right. So if you've got these horrible precipitation measurements, so the question is, do we just? Well, I can't deal with them, because we put these rain gauges out, and there's a lot of dust in Africa, and all of our rain gauges plug, and so then we have a break in the data. So then we have to send someone to Chad, and like clean the rain gauge, and so this was just a huge problem. So you're right. There's a lot to be said for consistent technology. By the way, all of our stations use consistent technology, and we change very, very conservatively. What we want to do is actually add our evapometer to the station. So we're not going to take away the existing data. We're going to add it to it. And so we believe in complementary technologies, so that if one fails, the other one might work. Yeah.
Two quick questions. Well, one's serious, one's not so serious.
Okay.
First, that horse in the desert, does it have a name?
It's not a horse in the desert. It's a horse with no name, but it's in Chile. It's in the Secano Interior. All I know is the patience shown by that horse. It was totally just hours, just standing there waiting for the guy to come back from lunch. Anyway, he's got a plow hooked up to him.
And then the second one is any of the technology or the designs you're working with utilize like traditional geophysical methods like seismic diffraction or ERT or GPR?
Yeah. There is one. We made a vertical sounding probe that you can pound into a riverbed that has 16 rings, and then we have a multiplexer which takes all possible combinations of those 16 rings and does tomography vertically through a riverbed. So that we made with the PNNL group, and then we put also 5 what we call osmopods. Each osmopod has an EC, a 4-wire EC circuit, a pressure sensor, and a temperature sensor. So we have 5 osmopods and then 16 rings, and we scan them all. And so we do have that tool. I can send you the undergraduate thesis. He's got a master. He's getting his master's and he's writing it up. And so it's a really cool project, and it worked out really well. I can show you some data from it if you'd like. Yeah.
You have me convinced that this is super important. I'm motivated.
Okay.
But I'm a modeler with no hand-eye skills. What is like a step forward?
Okay, collaboration. This is really important. And I think that this is a broader question of how you manage your career. Because we can manage our careers by saying, I see this really important work I want to do. And then you get drawn to something that you're really lousy at. And so this is a common outcome. So what you really need to be able to do is say, this is work which I am unusually good at, and I really enjoy. And if you enjoy something and you're good at, you're going to do killer work, right? So that's first off, that's your direction. Then, who do I need to work with to actually address the questions I'm excited about? So think about collaboration and never forget that your personal gifts and your personal imagination are fundamental. So you're going to collaborate, and that's going to be dandy. Yeah. Yeah?
Quick one. Did you tell the IEA about your new system? Because I think
it's in Vienna.
Showing the next system is the one that they recommend, right?
Yeah. No, we have our system in Vienna. It's being tested now.
So did you
I haven't.
make recommendation now at the...
Those data, that paper is under review. I mean, this is brand new data. But yeah, the IEA has our system. They've been testing it for like about 6 months. And yeah, I'm hoping that we get beyond. The isotopic rainfall collector.
Yes.
Yeah. Any other questions? Yeah.
I have like a general question. It sounds like you have developed solutions that can for multiple types of problems, and I just was curious about like whether you look for a problem that your solution already can fix, or do you how do you direct your efforts in research progress and topics?
Well, many of my colleagues wonder because it's not at all obvious. I kind of just do what I want to do. So the most recent example of that, between Iran and Tajikistan, there's this pass apparently where all the animals are herded seasonally and they beat up the grass. And this guy comes to me and says, hey, they wrap linen bags around the necks of the goats and it puts seeds out. Can we engineer this? So now we have accelerometers in a little seed dispensing thing, which we have 3D printed inserts to deliver the different seeds at different rates. And I'm totally excited about that. And so I tend to just if it's something I think we can contribute, first off, I look, is it going to be transformative? So it turns out that if we could auto-seed pastures around the world, it'd be a really big deal. Most growers want to get higher productivity seeds out there. And then is there an opportunity for engineering? There's only been 2 papers written on these animal-driven seeders that I've been able to find. One from the 50s and then one, and neither of them quantitative. So is there an opportunity for change and advancement? So I look, and then finally, do I have a special skill set? I didn't go through all this. I have a whole slide set on how you pick problems. But I have actually a set of criteria for selecting problems, and so I evaluate it through a set of 6 different filters, and then I identify if it fits my 6 criteria, then I do it.
So one quick question around the 3 device.
Yeah.
I would like how to get the details on the 3 device.
Which one of the 3 devices?
I mean, with your time bottles and.
Yeah. There's been actually a good number of publications now. So I can put you in touch with the publications. It's been published. And so it's been used widely. And so we've been working on that now for over a decade. And so it's a little bit of it's getting to be fairly much understood. Although there's still, the interesting thing about trees, small or large, 0.3 hertz. If anyone has an idea of why that is, 0.3 hertz. The trees almost all resonate at a very similar frequency, just regardless of 200 meters tall or 2 meters tall. So that's an interesting thing. So you can work on that. But no, anyway. So yeah, there's some interesting things out there. Yeah.
Maybe just rescale, right?
What's that?
The mechanic basically rescale. So then you can.
Well, there is some sort of fundamental. I mean, trees have the choice. They could be stiffer when they're small. They could be less stiff when they're tall. So I mean, yeah, this is for beer. You guys can just drink, it's like, oh. Any other questions? Good. Okay. Thanks very much.
Thank you very much.